physics is all about rules. This is what's happening for violating rules. Well, so we talk about relative motion, and this is what we've discussed yesterday. So I want to start from this question, which is very similar to the experiment we've done. In this situation, the moving plane is an equivalent of this moving paper. A passenger is modeled by this cart. Let's see if it works. Yep. So the plane is traveling to the right, and the passenger walks in the opposite direction. And again, we can help ourselves by marking locations. As we've said before, in any situation like that, we always have three objects involved in the process, in a phenomenon. In this situation, those objects are plane, passenger, and ground. In this situation, those objects are electric cart, moving paper, and the bench. And when these two markers move together, this distance is distance traveled relative to the paper. That would be the displacement of this cart relative to the paper. For the person on the ground watching what's happening, the displacement would have been different. And there's the displacement of this object relative to the paper. There's a displacement of the paper relative to the ground. And the displacement of the cart relative to the ground. And we already know the equation. We already know that for any three objects, oops, too soon. The displacement of the passenger relative to the ground should be equal to the sum. The displacement of the same passenger relative to the airplane plus the displacement of the airplane relative to the ground. In general, for any type of a displacement, we use symbol delta R. However, for a one-dimensional motion, we can replace R with X. We can just rewrite the same equation. I'm breaking my own rule. The rule says use the same letter for the same things and different letter for different things. So if I use ground again and again and again, I should use the same letter, either capital G or lowercase g, but it has to be the same. Now, what do we know? A passenger moves west relative to the airplane. So that's what we call west. This number, which represents this displacement relative to the positive x direction, should be what? Positive, negative, or zero. These are only options we have for real numbers. Negative. Now, which of these numbers is this for? First, second, or third? that should be of the passenger relative to the airplane. So these words, yes, we have to convert into symbol, and it's done with this. Now, the airplane moves 300 meters east. That's what we call east, right? So that should be the airplane relative to the ground. And normally, relative to the ground wouldn't be even a part of the text. We would have to assume that. So, which number is that? At this time, we just need to take calculator and calculate, right? Any questions? This is an illustration of the general strategy. The problem is simple, but everything is based on using this equation with the correct interpretation of each term. This equation has 3 terms. As long as we know how to correctly name or assign a number to each term, we can solve any related problem. So we've seen that, but again, in general, it doesn't have to be airplane, passenger, ground. It could be any 3 objects, and displacement over time gives the law which we've used. Now we're going to use this law for solving another problem, a standard problem about round trip. So you can read, but this is what is happening. Doesn't matter how we do it. So home, post office. Keep reading. Too soon. Too soon. Hey, you should work. Okay. I broke my glasses. My working glasses. Try this. Now I broke the card. Always have a backup. And ideally a backup for the backup. Something like that. Have you read? Finished? Have you? All right. Finished reading. So you move, turn around and move back, and everything was happening in the river. That's it. So how many different parts should we consider in this problem? 2. First time, no, the river cannot be read. First time, it travels in the same direction with the stream or up it and vice versa. So that's the river. First time, home, post office. Post office has a roof. Stream. The velocity of the river relative to the ground. I pointed it to the left. Doesn't matter. The boat travels, well, technically there's two different velocities we can assign to the boat. The velocity of the boat relative to the river. The velocity of the boat relative to the ground. And a second situation, still same velocity of the river relative to the ground, but the boat wants to go back to the home. So we still have velocity of the boat relative to the river, and still velocity of the boat relative to the ground. Now we get some numbers here. This. Well, of course, distance is the same for both parts of the trip, right? Now, in a lake, your boat travels at 15 kilometers per hour. Please tell me, to what velocity does this number refer? The magnitude of a certain specific velocity should be equal to this number. Magnitude of what velocity should be equal to 15? Exactly. It doesn't matter if it's relative to the still water or moving water, it's relative to water. In this situation, river. So this is this term covered. Now, 5 kilometers per hour. This is the speed of something you drop in water and it drifts with water. So 5 kilometers per hour, that would be the magnitude of what velocity? Relative to ground. Now, in real life, every day we just say velocity or speed, but we need to understand that it's a slang. The full name always has eight words. Velocity of this object relative to that object. That's the full name. It's like if you call me Mr. V, that's slang. My actual name is Valentin Viktorovich Voroshilov. So, the velocity of the river relative to the ground. And we call it RG. So, which velocity is related to time of the travel? Not that, and not that one. Relative to the ground. Yeah. If we want to write the speed of the boat relative to the ground should be equal to the distance measured on the ground divided by time travel relative to the ground. So it's very important to remember every time when we write an equation like that, which relates several variables, they all must be related to the same origin, to the same reference frame. If distance is measured relative to the ground, then time, of course, well, in this mechanics, time is absolute, so it doesn't depend on reference frame. But as we saw, distances and velocities depend on the point of view. So, boat relative to the ground, distance measured on the ground. Now, this equation, of course, we can write twice. First time for the trip, well, up the stream, and second time for the trip backwards, down the stream. And in these equations, the distance is always the same, 20 kilometers 20 kilometers. So the real question now is, what numbers should we write here for the speed of the boat relative to the ground on its way up the stream, and what number should we write here for the speed of the same boat relative to the ground, but on its way down the stream. So here, let's see. No, okay, I can move it. No? Yeah. Please tell me this number. Yes. Why? Are you agree? So you're absolutely correct. That's what our intuition tells us, but we also can use the rule. So how would we use the rule? Well, here we have, if it's an arrow, that's the velocity of the river relative to the ground, and this is the velocity of the boat relative to the river. And there is also the ground. So these are objects. If we want to use, and if we want to get a habit of using this rule, we need to name objects 1, 2, 3. We have to make a transition from a specific situation with specific objects to a general, abstract situation. And of course, it wouldn't matter what we call number 1, 2, 3. From my experience, it's easier for us to look at everything relative to the ground. So the last digit I usually assign to the ground. So the ground I call the object number 1. And the boat is traveling relative to it, so I call the boat the object number 3. Automatically, the river becomes the object number 2. But again, it doesn't really matter in the end. Now I can rewrite this equation using my specific objects. Yeah? The velocity of the boat relative to the ground should be equal to the velocity of the boat relative to the river plus the velocity of the river relative to the ground. And at this point, we need to remember we're using vectors. We are adding vectors. That's what we're doing. This vector, which is 5 kilometers per hour long, we need to add with this 15, sorry, boat comes first. We need to add with this vector, which is just 5 kilometers long. If we need to add two vectors, what rule should we apply? What's the name of the rule? Yes, 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 yes. No. Head to tail. We could have used components, but that would be too much work, because everything we need to do now is just draw two arrows together. So this gives us the new arrow, which is velocity of the boat relative to the ground. Now, the length of this arrow, as we can see from this picture, is equal to 15 plus 5. And that's how we get 20 kilometers per hour. So, and in that situation here, what number should we write? Ten. Any questions on 10? Well, so T1 will be equal to 1 hour, 20 over 20. T2 will be equal to 20 over 10, 2 hours. So your total time for the round trip is 3 hours. Any, yes? Well, I just asked any questions on 10. So we always have to stick to the strategy. The strategy depends on what phenomenon we need to study. For example, if you shoot a ball and it flies like this, using the law of relative velocities wouldn't be really smart, right? Choice to make, because they're not related. So that's why names are important. The name of the phenomenon excites the right memory cells. This is what we call projectile motion. And I've got one more problem with this. And for projectile motion, we need to start from writing motion and velocity equations, which is supposed to be a part of your equation sheet. But I would suggest it's supposed to be a part of your memory by now. So this phenomenon has a name, relative motion. That's why it's important to know, because, you know, if you name your friend with a different name, you're not friend anymore, right? So if you name a phenomenon with the wrong name, that's it. You just cannot apply the theory behind it. So if you look at what's happening, you name it correctly, relative motion, you know what law to apply, the law for relative motion. And now you just have to apply it. Application in physics always starts from drawing a picture which shows clearly what's happening. Now what's happening? The river still travels in the same direction. So the velocity of the river relative to the ground, the magnitude of this is still 5 kilometers per hour. But the boat now travels in an opposite direction. This is the velocity of the boat relative to the river, but the magnitude of this velocity is still 15 kilometers per hour. So now we need to combine that specific situation with that general, or we can say generic law. To do that, we introduce numbering. And again, it doesn't matter what number we assign to boat, river, or ground. But from the point of convenience, the ground is usually called number 1. The moving object usually is called number 3. And the middle object, river, wind, automatically will be called number 2. So now we should write again. The velocity of the boat relative to the ground should be equal to the sum of the velocity of the boat relative to the river and the velocity of the river relative to the ground. And if you remember what we've done just a minute ago, so far there is no absolutely difference between what I've been writing 5 minutes ago and what I'm writing now. The difference is not in equations. The difference comes now when we start using the equations, because we need to add 2 vectors, boat relative to the river plus river relative to the ground. That's what we need to do. So by now, either you're familiar with vector additions, in that case, everything is clear, or you may do some more exercises on vector additions to make it clearer for you. So we can apply components, or we can use a tail to a head rule. And as the result. My resultant mathematically it's a vector which connects 2 points beginning and end. Physically, this is what we call the velocity of the boat relative to the ground. Geometrically, see how much things do we use. Now we have to use geometry. To calculate the length of the red arrow, we now have to subtract 2 numbers. We have to do this, right? This is what we call vector addition. But if we make a transition from vectors to magnitudes of those vectors, turns out in this particular example, we kind of adding a negative number, subtracting. So it's 15 minus 5, 10. So I want to point at the fact that starting from the very first equation to the very last result, very last number, I didn't use my intellectual abilities at all. I wasn't thinking. Here, I need to think. When I had to choose, what set of equations do I need to use, which depends on the phenomenon. And name of that phenomenon helps me to make a choice. After that, it's just automatic work. A robot can do that. Well, if we teach the robot properly. Questions? Again, yes, this is very common strategy. Phenomenon, picture, selection of the correct connections, mathematically connections described by certain equations, some mathematics. Yes?
So I was going to ask, like when I set it up, I have one direction being positive and the other being negative. Because we're using just the magnitude at the end, it doesn't matter, right? One of my speeds came out negative because it was going negative.
Just a second. And your question? Yes, exactly. But on its way toward the post office. And this is a situation when it travels back from the post office to the home. Now, your question comes from the difference between magnitude and component. In my calculation, from the very beginning of the problem to the very end, I haven't used any component. That's why I don't have any negatives. I used geometry. But you could have used components as well. Components would give you what? Well, how do we make a transition from vectors to components? We just rewrite the same equation, but instead of using a symbol for a vector, that little arrow, we start using a symbol for axis. This is the equation, BRGX. Like you did in the homework, the equation which relates vectors automatically relates components. I can even write like this. The same equation will work for y components. However, in this situation, all y components are equal to 0 because these vectors don't have them. But here, what do we have is, well, this is our unknown. That's what we're looking for. And here we need to write 2 specific numbers. What is the x component of the velocity of the boat relative to the river? In this situation, it's negative 15 because it points to the left. What is the x component of the velocity of the river relative to the ground? In this situation, it's negative 5. So as the result, the x component of the velocity of the boat relative to the ground will be negative 20 because of this. Everything points to the left. But if you want to relate distance time, we need to use speed, not velocity. So if velocity points to the left, the magnitude of it's still 20. So the equation still magnitude of the x component of velocity of the boat relative to the ground should be equal to distance over time. Well, that was time number 1. So again, it doesn't matter if we use component method or we use drawings. And you should use both again and again to get the feeling which would work for you, like faster or more convenient. It's only a matter of convenience and practice. There is no one single best approach. It doesn't exist. You look sad. Oh, not anymore. Well, now we're going to talk about two-dimensional situations. First, again, we need to see the difference between the actual two-dimensional situation and like quasi, pseudo, by a choice. Here, the projectile motion is the actual two-dimensional situation. Why? Well, because the trajectory is not a straight line. By definition, a one-dimensional motion is motion when trajectory is straight line. If it's not, that's it. But here, this is a situation when an object moves like perpendicularly or at a certain angle toward the stream or flow. In this situation, the trajectory is straight line. So technically, this is a one-dimensional motion. We could have drawn the x-axis, and that's it. However, for simple reasons of convenience, it's actually easier to treat this one-dimensional motion as a two-dimensional motion. So first, a quick recap of the actual two-dimensional motion. One more problem on projectile motion. A very common situation. So an object, a ball, is being launched from the ground. Would it make a sense to use a law for relative motion, relative velocities law, to describe this situation? What do you think? No, not really. So don't do that. If we talk about projectile motion, we should write equations for projectile motion. We have two sets of those equations. One for a horizontal part of the motion. And basically that's it. And second for the vertical part of the motion. And at this point, again, this action, this is action. We call it writing. Yeah. It requires hand movement. It doesn't require thinking, right? So I'm proving you again and again. There is not much thinking in physics. Everybody who tells you you need to think a lot in physics lies. That's the motion equation for the vertical component. And of course, there's the velocity equation. The most important, the crucial part is to remember that now these variables, v here and v there, represent different components of the same vector. here, that's the x component of velocity. I could have, well, technically, this is what I should have written. The x component is equal always to its initial value because it doesn't change, because it is constant. But the y component changes. So this symbol represents the y component of initial velocity, same as this. And now we just need to, yes? Do you think I remember? I don't remember. I have to look at the slide. That slide excites right memory cells. Those signals travel to the throat, and it starts saying something. I have no idea what it says. So this is the x component of velocity, which is constant. It is always equal to the initial value of the x component because it's constant. When something is constant, it's always equal to its initial value because it doesn't change. However, y component of velocity changes. The initial value of y component of velocity, well, might be positive, might be negative, might be 0, but due to gravity, it changes. So in these equations, this variable v sub y naught here and here represents the y component of initial velocity. We could have said it represents the initial value of y component of velocity, but that would require more words. But that would be exactly the same thing. So y component of initial velocity. Where do we see them? Well, right here. This is the x component of initial velocity, which remains constant. This is the y component of initial velocity, which changes. And the point I want to make actually is this. As we know very well now, a vector and its components always form a right triangle. So as long as you see a triangle, physics is done, geometry starts. You can write 2 more equations just from knowing how to solve right-angle triangle. For example, the x component in this situation will be equal to the hypotenuse times cosine of the angle, which is 40 degrees. The y component, and I can't stop saying anything, I can't stop speaking, I have to say the y component of initial velocity will be equal to same hypotenuse times the sine of the same angle. And now it's done. Now it's solvable. Now we know everything. We can calculate these components immediately. And if we know those components, again, what can we do? Well, we know the fact that at the highest point of the trajectory, right here, the y component of velocity momentarily, instantaneously becomes 0. Hence, we can use the velocity equation, which says the y component of velocity is equal to the y component of initial velocity minus gravity times time up, which means 0 should be equal to, now, if we go back, what number should I write for the y component of initial velocity? 16.85 or 14.14? First or second? The y component of initial velocity, second, 14.14. This number comes here, minus 10. If we do homework, we don't use 10. Yeah, for homework we use 9.8 times time up. Time up is equal to 14.4 over 1, 1.44 seconds. All right. Since it's Wednesday, I'm going to write an actual 4. Now, since the object goes up and down, exactly the same height, it's very easy to see that time down in this situation will be also equal to 1.44 seconds. Same time up, same time down. Every time when the projectile lands at the same level where it starts, time up is equal to time down. Total time will be equal to time total 2.88, because we just need to add them up. And now you can calculate maximum height. You can calculate the range if you want to. Well, my slide uses 9.8, so it's, instead of 2.8, it gives 2.9. And this is how we can calculate the range. The range is how far it travels horizontally. So for horizontal motion, we need to use 18.85 or 16.85, and total time. This is 0, as we know, because the acceleration has only one component, which is negative relative to our choice of positive y direction. In general, when a vector is perpendicular to an axis, it doesn't have component to that axis. For example, acceleration is perpendicular to x-axis. Ax equals 0. The velocity at the top is perpendicular to the y-axis. V top y equals 0. Any questions, please? You know, it's going to be posted on Blackboard. Plus, it's being taped right now. Although I haven't checked, actually, so far. I just believe it's being taped. So, all right. Now we're going back to this quasi-pseudo two-dimensional situation. Please read first. Because soon I'm going to switch to the document camera. But what's happening here is this. Let's assume this is a lake. Always have a backup. Now, what difference would we see if that would have been river? Did I broke it too? So, did you see the difference? Now the question. What does aim mean? This is, I aim the boat right across the river, which means I aim the boat at 90 degrees to the stream. I could have aimed it this way. So I see a tree over there, and I aim my boat at that tree. I could have aimed at this tree. I see the bush, and my friend hiding behind it. So I want to aim at my friend. That's what aiming means. But there is a difference between how you aim it and how it actually travels relative to a friend or a tree or a bush, right? And that difference might affect, including, well, among everything else, time. How much time would it take to actually reach the opposite shore? So, by now, you need to make your decision. How do you aim? Angle. Angle, aim, synonymous. 1, 2, 3, 4, 4 choices. Pick one. Write it down. Enter in the WebAssign. Too late. So I just want to show different possible options. Again, aiming right across. If we aim right across, relative to the ground, this will be the actual displacement of the boat. So this would have been the displacement of the boat relative to river. This is the displacement of the river relative to the ground. Displacement of the boat relative to the river plus displacement of the river relative to the ground is equal to the displacement of the boat relative to the ground. Now there's another kind of extreme situation. If I manage, well, okay, first, if I manage to drag it too fast, still it might land below the original point. But if I manage to keep exact the certain speed, we can see that the boat had crossed the river at 90 degrees, so it lands right across the initial location. But to achieve this motion, this arrow now represents the actual displacement of the boat relative to the ground. To achieve that, I had to aim it at a certain angle to the stream, actually opposite to the stream. Right. So depending on how you aim, the time will be different, because time is related to the actual distance traveled, right? So you have one last chance to look at the question. One last chance to enter your answer. I just want to take a look at the distribution. Well, 2, 3, 4, that's a wide distribution, which is a good thing. 2, 3. Well, let's think about it. Let's say river flows. Well, we call it north, we call it up, and that is the velocity of the river relative to the ground. You start here. Well, we have 3 options in general to aim the boat. Something like this, something like this, something like this. Yeah. And here is where it's kind of convenient to treat this motion as a 2-dimensional. For all three options, this will be the same number. This distance between two shores, we call it Lx, for example, will be the same. Now, time to travel supposed to be related. On one hand, we can always write an equation. Speed should be equal to actual distance traveled divided by time. But also, since we know how to use vectors, we can write that the x component of that should be equal to this divided by time, as well as the y component of that should be equal to Ly divided by the same time, if Ly exists. So it could have been something like this. If it lands here, that could have been Ly. But the difference between these equations is that this equation is easier to use to figure out what to do to cross as fast as possible. And then this equation is more convenient to use to figure out the distance dragged by the stream, if that even happened. So now, please, if you look at this equation, to minimize time, to travel as fast as possible means make this number as small as possible. To minimize time, keeping this distance constant, what should we do to the x component of velocity? Increase, maximize to make it as large as possible. And now we need to keep in mind a very simple fact. It doesn't matter how you aim your boat. It's still the same boat with the same engine. So it provides the same speed relative to water, just in different directions. So when you use this picture, this velocity, or this velocity, or this velocity should have exactly the same length, because it only depends on the engine. So which arrow from these three, 1, 2, 3, gives the maximum value for the x component of the velocity? Number 2. So the answer is, this is how you should aim your boat if you want to cross the river as fast as possible. But there's always trade-off in the life. You win something, you lose something. So if you cross the river as fast as possible, you're being dragged down the stream. If you don't want to be dragged down the stream, you have to aim your boat up the stream. In that case, you travel by the shortest distance, but that would take more time. So it's always a choice, shortest distance or fastest trip. The answer is, yeah, shortest time, shortest distance. And there's a YouTube movie you can watch. It helps. Now, of course, we just have to solve a couple of problems. Well, this slide represents the summary of everything I've just said. Two different situations. Shortest time, you have to aim your boat perpendicularly, but you've been dragged. Shortest path, shortest distance, you have to aim your boat against the stream. In that case, you travel across, but it takes more time. And as you can see again, the equation is the same. The equation cannot be different because the equation is just a law for a situation when something is moving relative to anything. Now, what do we do to use that equation? We use triangles. The velocity of the boat relative to the ground has to be equal to the velocity of the boat relative to the river plus the velocity of the river relative to the ground. This equation, again, is the same for both. What is the difference? The difference is only in the picture. Because in this situation, this is the velocity of the boat relative to the river. That's how we aim it. So this velocity in this triangle is the hypotenuse. But in this situation, this is how we aim it. And the velocity of the boat relative to the river now represented by just the short side. So if you see that, the rest is just sine, cosine, or tangent of Pythagorean theorem. Like in this example. Fastest trip. So we want to travel as fast as possible. That means we have to aim like this. This should be the velocity of the boat relative to the river, but due to the stream, we are being dragged down. This will be the actual velocity of the boat relative to the ground. So this is our schematics. Let's say we start here. This is how we would have been traveling in a lake if there would be no stream. However, in reality, due to the stream, we land somewhere here. This is the actual displacement. So this is what we call Lx. This is what we call Ly. This is some kind of an angle, which probably we need to calculate. But the good thing is velocities also form right triangle with exactly the same angle. This plus this equals this. Well, this is velocity of the boat relative to the river, velocity of the river relative to the ground, the velocity of the boat relative to the ground. So now, this is equal to 1800. How do I know? Well, first of all, I'm human, I can think, I have eyes, I can see, and I'm educated, I can read. See how many things involved. It's important. Now, where else do we know? In lake, it would have been traveling at 4. So, 4, what number? What velocity should I use? Yes, that's 4. The river, so now we're done. Yeah, all we have to do is just, well, let's call this again theta. So angle theta will be equal to inverse tangent. I'm doing inverse tangent of opposite over adjacent, and the actual speed of the boat relative to the ground will be equal to square root of 2 squared plus 4 squared. And if you want to calculate time, we have several options, but again, I prefer using x components, so time should be equal to Lx over magnitude of Vx, which is actually Lx over velocity of the boat relative to the river. That's the in fact, this velocity, physically, that's velocity of the stream relative to the ground, but mathematically, it also represents the y component of the actual velocity of the boat. So that's going to be, well, 1800 divided by square root of 20, wherever it is. This will be equal to, well, the speed of the stream times time. That's it. As long as we draw the correct right triangle, I would say, as long as we draw the right triangle, we're all set. And the question is answered here. Well, use Pythagorean theorem, one of the approaches. The second one would have been, yes?
In the last slide, where did you get square root of 20?
4 squared is 16, 2 squared is 4, 16 plus 4, 20. Yes?
If you're using 1800, don't you think it will so you used 1800, which is the width of the river, rather than the...
Absolutely correct. You see, I wanted to trick you, but I didn't. You've been paying attention. Oh, maybe I forgot. Or maybe it's Wednesday. Or maybe it's coffee. I just said it should be Vx. Excuse me. Or not. I need to wait until all drawings will be placed in the slides, or I will lose everything. All right, we're good. So you're absolutely correct. Now, question. All right, I'm going to do this. 4. Oh, yes, that's why I did it. Because it's Wednesday, I'm writing actual 4s. All right. And that should be a 2. Okay, I think everything else is in. That's what I meant. For this speed, for this speed. And actually, what I wanted to say now, that's what I meant. Yeah, if you know this speed, there is another way to calculate this distance, because this is the actual distance. For the actual distance, you can use the actual speed of the boat relative to the ground times the same time. So we always have more equations than we need to answer the same questions. More. So you can use either geometry of a horizontal and vertical axis, and right triangle for the x and y components of the displacement, or you can use the relationship between distance, time, and speed, but you need to use the correct speed. Either way works. Shorter strip. Well, for the shortest trip means shortest path, we know that we have to aim opposite. That's it. That's all we need to know, nothing else. This arrow represents the velocity of the boat relative to the river. This arrow represents the velocity of the river relative to the ground. If we add them up all together, this arrow plus this arrow, that's supposed to be the arrow which represents the velocity of the boat relative to the ground. In this situation, that arrow must point straight across the river. Start, finish. So our triangle now looks like this, this, boat, river, ground, boat, ground. Now, well, of course, some kind of an angle. This is how we aim it, theta. Now this theta will be equal to the inverse tangent of the velocity of the river relative to the ground divided by the velocity of the boat relative to the ground. But if we write it like this, we don't know this yet. So we can do it different. Well, we can use the Pythagorean theorem and calculate this. For example, if we use the Pythagorean theorem, the magnitude of this short side should be equal to hypotenuse squared minus another short side squared, and that immediately gives us 4 squared minus 2 squared. Now it should be 16 minus 4, 12 meters per second. Or we could have used sine. Theta also should be equal to the inverse sine of opposite over hypotenuse. So that's the inverse sine of 2 over 4. Any questions? Yes. I just can't trick anybody today, despite my best effort. Well, same distance, okay. Well, immediately we can answer a question. In this particular situation, what number would I, well, should I actually use for the displacement along the shore? Is it being dragged? No. So what number do we use for no? 0. In this situation, the actual displacement delta r looks like this. So the displacement doesn't have y component. So where does the boat land? Well, right across. That's it. It's not being dragged. How long does it take to cross the river? Well, we need to use variables related to x component. So it should be this velocity, the actual velocity relative to the ground should be equal to this divided by time. So time should be equal to this distance divided by this number. And if we use our calculation, that now should be equal to 1800 over square root of 12. Wherever it is. That's it. Any questions? All right, I've got 6 more minutes to cover 20 more slides. Now we're going to start talking about reasons for the motion. Well, we know everything about that since 1687. First, when we start studying something new, we need to introduce new physical quantities. We need to name something which is important and specific for that particular phenomenon. And that new physical quantity we're going to study has a name, force. We know many forces. For example, force of gravity pulls everything down. It stops because of friction acting between this object and the surface. If we attach something to a spring scale, there is elastic force acting. Forces we can divide into categories. One, we call contact forces. The word contact is a fancy word for touching. When two objects touch each other, they are in contact, they influence each other. But gravity, magnetism, electric force, they don't require touching. Now, there are many, many forces. We're going to start from a set of simple mechanical forces. For example, a very standard experiment. We know that the gravity pulls it down because if I lift it and let it go, it falls down. But when it sits on the table, why? There is a force which is acting from this table and which opposes gravity. That force, which prevents something from falling, has a name, the normal force. And in physics, the word normal is not opposite to abnormal. In physics, normal means perpendicular. Write it down. If you see normal force or normal vector or something normal, it means at 90 degrees to the surface. Normal force always is perpendicular to the surface. Now, gravity, normal. If I pull on a string, That we call force of tension. I can push. That we call just applied force. It has no name. And again, if I gave it a push and don't touch anymore and it stops, friction. All important forces. Now, there is only one equation for today, that equation for calculating force of gravity on the surface. So if you know how much it weighs, about 2 kilograms, that's what we call mass, that's what we read on scale. Mass times g is equal to force of gravity acting on this object. So if it's 2 kilograms, 2 times, well, 10, roughly, 20. 20 what? Well, we have to use international system of units. If we use this equation, the unit of force, remember lecture number 1, should be equal to the product of the unit of mass and the unit of acceleration. For the mass, we use kilograms. For acceleration, meters per second squared. So that's a kilogram times a meter divided by a second squared, a unit of force, bless you. But this unit has a special name. Of course, Newton. Now we can see, again, a very common situation when exactly the same letter is being used differently. Capital N here can be used as a unit of a force, but also very often it's used for the magnitude of the normal force acting on an object. Newton left us many, many laws. We start from the third one. The third Newton's law says when two objects interact, they exert forces on each other. Those forces have exactly the same magnitude, but opposite direction. For example, here. Oops. That's the trickiest part of this experiment. I might spend the rest of the time. Okay. Sixteen. But of course, they act in opposite directions. So this is the Newton's third law. It's not a definition. Theoretically, we could have redefined a definition and make everybody agree. We cannot change the law. The law is not up to us. The law just comes from nature. We just have to remember it. When two objects acting on each other, they exert forces on each other, opposite but same magnitude. That's it. There are many situations when this law can be applied. Two objects collide, push on each other. If we let the ball fall, well, first of all, right now, two forces acting on the ball. Gravity, because Earth attracts everything, and my fingers, technically it's friction between fingers and the ball. But if I remove my fingers, it's going to fall down, gravity. Why does it bounce back? Because when it touches the table and exerts a force on the table, it means one more minute. The table, just to finish the sentence, the table exerts a force on the ball, and that force makes it bounce. That's not a question, just final statement. In this experiment, you have an object, and you have a very strong person pulling on the rope and a very weak person, a boy, pulling on the rope. They both exert forces, strong, weak. But we know that in reality, if we exert two forces, strong and weak, the resulting force is neither. Actually, all experiments demonstrate that the resulting force is just the sum of all forces. That's why we've studied vectors, because today, tomorrow and on Friday, you will be using this law in a lab. The sum of all forces just has a name, the net force or total force. And now we're done. Thank you very much. Still.
Yeah, that's fine.
Okay.
Thank you very much.
Yeah.
So I'm also not here this Friday, and we have the lab, right?
You could do it on Thursday.
Thursday? What on Thursday?
Well, Thursday we have a lab from 11 to 2:30. Can you do it on Thursday? Or can you do it on Friday, different time?
No, I fly out. I'm flying out Thursday afternoon.
How?
What? I can look-
When afternoon? Oh,
I think I have a flight at 12:30.
send me an email. I'll figure out something.
Okay.
No, you gotta go that way. And you can take this. Thank you. I can't do it yet. Yes.
There's still a lab session tonight, right?
Tonight, yes. Today is Wednesday. It's a regular Wednesday.
Okay.